everyone, and welcome. Today's topic for the webinar is remote workflows at ALCF. And I'm going to just stop my camera for the duration of the talk. Yes, today's topic is remote workflows at ALCF. I'll just, oh, here we go. Okay. Begin with a brief outline of what we'll be covering today. First, we'll begin with some motivation for the reason we are thinking about and running workflows that are triggered from outside of the facility on our machines. And I'll be talking about our approach for executing these remote workloads. Then I will talk about a bunch of tools that we are using here at the facility to facilitate this work that are provided by Globus primarily. So we'll be talking about a number of different tools that they have in their software stack for executing remote work. We'll talk about Globus Compute. We'll talk about how to set up what are called compute endpoints on ALCF machines to run Globus compute functions. Then we'll talk a bit about Globus Flows, which is a remote workflow orchestration tool that Globus provides, and then we'll just go over some conclusions. Okay. So, to begin with some basic motivation, what we're going to be talking about today is triggering workloads from on our machines, but from outside of our machines. So probably many of you are familiar with running work on our systems or other HPC systems where you might SSH into one of our machines in a shell, and then you interact with the scheduler on in your shell, submitting jobs to the scheduler, looking at data on the file systems, things of that nature. Now, if you wanted to do all of that type of work, but do it on a shell on your laptop, for example, or maybe from a computer at another facility, say the APS, which is an X-ray light source here at ALCF. So we are seeing that we have an increasing number of users that have workloads that need to be triggered in this way. And the typical types of use cases for this work, a lot of it is work from experimental facilities, like, as I referenced, X-ray light sources like the APS. But we're also working with tokamak experiments, neutrino experiments, and others. And then we also have a set of remotely triggered workloads that are in the area of AI and ML inference tasks and services. So we have this project called Aurora GPT, and which is a planned LLM service that will run on our machine Aurora. And that type of workload is, you want to be able to have users sending requests from outside Aurora to get, inference results back from a service like Aurora GPT. So these are some of the areas where we're thinking about and working on these types of workflows. And I guess I will say, this kind of pattern or capability could be of use to any user that wants to coordinate work across multiple facilities or machines. Say you have workloads, you have time at both ALCF and OLCF, for example, and you want to be able to, drive the work you run there from a single location. Like, you could maybe use tools like this to enable that kind of work, and we've done that in the past. Okay. So as I referenced, some of the work that is being done in this area on our machines is in the context of computing for experimental facilities. So I just wanted to highlight that that's not just an effort that's happening at ALCF. This is something that's happening across the DOE and DOE computing with the new IRI program. And this is just a slide describing the sort of vision of that program, where the idea is we have experimental and observational user facilities like X-ray light sources, tokamaks, genetics experiments, things like that. And we want to be able to connect them to advanced computing, such as what we have here at ALCF. And as I referenced before, one of our biggest users in this area is the APS at Argonne. And this is an X-ray light source on campus here at Argonne, where you have around the ring of the light source different beamlines. And each of these beamlines will be collecting data, and they need to do compute on it. So how do they do that? And many of them are doing it on our machines. And so they use the tools we'll be describing today to send those data to our facility and run compute jobs on them. Okay, so I've said this is possible, that you can remotely trigger work. I've not really said how this is possible. And for those of you who are experienced in HPC, it might seem maybe surprising or confusing how this even should be possible. So I'm going to just talk very briefly here about the overall approach for how we trigger remote work. And this is sort of describing a general pattern that we've used with a number of tools now. We'll be focusing on Globus tools today, but we've used this sort of general approach with a number of tools, including an in-house tool called Balsam in the past. So the main challenge for triggering remote work is you need to be able to communicate with the scheduler of the machine from the outside. Now, how do you do that? Well, the approaches we're going to discuss today rely on a user starting a process on a node, say a login node, that has access to the scheduler and can also make outbound connections from the machine to some kind of remote service or database where the work is defined. And so in this model, in this diagram, can you see my mouse out of curiosity? No? Can you see my mouse now?
Yes, yes.
Okay. A user will send tasks to a remote service like Globus, or it could be the Balsam server as well. And then you have a process running on the login node that will reach out to that service and pull those tasks down. And it will look at the tasks that it receives and decide how to run them. And this process that runs on the login node will then submit batch jobs to the scheduler, which on our machines here at ALCF is PBS, but other machines at other facilities might use Slurm. It's the same thing. And then, PBS will do what it does. It will submit work to compute nodes. And this is the sort of overall approach and pattern we have for executing these remote workloads. Okay, so I'm going to begin by talking about Globus Compute, which is a tool for executing remote functions remotely through the Globus service. What is Globus Compute? It is a tool, it works on a fire and forget model, where it allows users to launch applications on ALCF systems remotely from a laptop or any other external machine. What the functions it sends are Python functions. So this is a Python-based tool, but you can wrap any compiled executable with a Python function. And I'll show an example of that. And you will send these functions through the Globus service to a process running on the target machine. That process is called a compute endpoint. And to run tasks through Globus Compute, it requires the user to set up a compute endpoint on, say, Polaris, or in the future, maybe Aurora. We'll be looking at how this is done, but I will mention Globus Compute is built on top of a common workflow tool called Parcel. And if any of you are familiar with Parcel, some of the configuration options might look very familiar. And that's because the compute endpoint is essentially running a Parcel workflow to execute the tasks it receives. And we'll talk in the second half of the talk about how you can incorporate Globus compute functions with other data management tasks with something called Globus flows. So let's just start with a very basic example. Say you have a task that you typically run within the machine through a normal type of batch job. And this is something hopefully we're all familiar with. And I'm going to show you how you can translate this very simple example that you would run internally on the machine and be able to run it entirely remotely through the Globus service. So for this example case, you're executing a compiled executable called Hello Affinity on a single GPU, and we pin it to the GPU by setting this environment variable CUDA visible devices. Polaris has NVIDIA GPUs that use CUDA. So in this batch script, you have some PBS options, and these are the things that tell the scheduler how many nodes to get, what project to charge node hours to, and other options like the queue, file systems you need, etc. What we will see is we're going to kind of split the content of this script into two pieces. One is the configuration for the Globus compute endpoint, which will contain all the information that your typical batch script has for communicating with the scheduler. So all your PBS options will end up in your Globus compute endpoint configuration. Then the details of how you execute the application within the job, that will be translated to the compute function, which is a Python function. And I will show you how that is written as well. And if you want to try this out for yourself, there are some materials in our fall workshops materials on this example of running this application, Hello Affinity, through a Globus compute endpoint. And you can click on the link here and pull down all the scripts to test this out yourself. And I should say this application, Hello Affinity, comes from our Getting Started repo, which some of you might be familiar with. So first I will talk about how to write the function. Now, if you are executing native Python code, that's actually much simpler in a sense. You can send that function of native Python code directly through the service, although you do have to make sure that the environment running the endpoint has access to all the libraries that you need to execute that function. But I'm going to show you here a slightly more complicated example of how you execute a compiled executable. And in this case, Hello Affinity is a little C++ program that just reports things about what GPUs and CPUs it is running on. So what you do in this case is you define your wrapper function. This is called Hello Affinity wrapper. And within this function, you'll use Python subprocess module to launch the command. In this case, this will be a path to your executable on the file system of Polaris that will, execute this, that you want to execute, essentially. And you will launch this, this command with the subprocess module function run. And this is what it looks like here. You might want to also capture aspects of how this executable runs, for example, the standard out and standard error. the return code, things like that. That information will be contained in this variable res. And here I show you an example of how you would write out the standard out and standard error to a file containing that information into a file called hello out. And this should be written to a path in the directory where you run this. And the run directory in this example, we pass as an input to the wrapper. And so this run directory in the batch script example, we just CD'd to the PBS directory where you submitted the job. In this case, we pass the directory where you want it to run as a variable, and then we just we make that directory if it doesn't exist, and we move to that directory to run it. And then when we write out our standard out and standard error, that's where it should end up. One thing to point out is that any Python libraries that are required to run this function, in this case, the subprocess library and the OS library, they have to be imported within the function itself. That's very important because essentially the way this function is communicated to Polaris is it's serialized and sent through an HTTP connection through the Globus service down to your compute endpoint. So it needs to have a complete, all the information it needs to run the work contained within it. So you cannot, for example, put this import subprocess or import OS in the lines above where you've started the definition of the function. Okay. How do we then run this? Okay, so this is an example of a script to execute this function on a remote machine like Polaris, but you would execute it from your laptop or any other machine that is not the target machine. What are the elements you need to provide? First, the function, and I've just abbreviated the script here. This is just imagine it containing what's on the previous slide. Then you need to give it some information about the process running on the target machine, maybe Polaris, where you're sending this function. And in Globus Compute, this is something called the endpoint ID, and it's a UUID. This looks like a random string of numbers and letters, and it is, but we'll show you in a minute how you set up the endpoint and where you get this ID from. But you need to have it in your script sending the work from the remote machine. And then you need to create a client pointing at this endpoint ID. And this is pretty simple with the Globus Compute client. You create it in this way. And then you can create as many tasks as you want running this function, Hello Affinity Wrapper. Here I created 4 tasks that will run this wrapper function, and they will all print their standard out and standard error to unique directories on the file system. This path here is going to be a path on the file system of Polaris. So I did it relative to my home directory, but you could do it to any path you want on the target machine. And then what is returned in this task object is something called a Python future. This is a proxy for the completion of the task that may or may not have yet been fulfilled. So essentially, once you run this, client.submit function, what happens in the background? This function gets serialized. Its inputs, the serialized function and the inputs get sent to the Globus service. It's being sent with a client pointing to this endpoint ID. So then the Globus service will send this to that endpoint running on your target machine. And essentially, then your endpoint will submit a job to the scheduler of that machine to execute these functions. The future objects then during this whole process will not contain a result yet, but you can wait for those results to return to you by calling this task.result here, t.result. So essentially, if you execute this on, say, your laptop, the work will be sent off, and then in this particular case, the script will wait until the results are returned back to it from the compute function that's executed on the remote machine. Okay, now I've said a lot about, and I've alluded to compute endpoints, but I haven't really described how you set that up, what is it? So now we'll talk about that. So what we're going to discuss is how to set up this process that will run on, say, the login node of Polaris that will communicate with the Globus service and pull down functions to run on Polaris compute nodes through the scheduler. So to do that, you need to, and this is some of this is a one-time setup essentially. You need to log into Polaris, and you need to configure and start the endpoint. And we'll talk about now what that is. So to do this on Polaris, what you need is an environment, either a Python virtual environment I've done here, but you can also create a Conda or a Mamba environment where you can pip install this tool, Globus Compute Endpoint. Once you have that installed, using that environment, you will configure the endpoint, and you'll do it with this command. And you need to give it a configuration file, which will be a YAML file with a bunch of options. And we'll see an example of that in a second. But suppose you have that file, you will configure the endpoint with your config file, and you will call it my endpoint. This is the name of the endpoint now. Once you've configured it, you need to then start it. So all you've done is you've created essentially a space on Polaris where you have a bunch of configuration options. But then to actually start the process that can talk to the Globus service, you then execute this command here, Globus compute endpoint start, and then the name of the endpoint, my endpoint. So once you've done that, you can query what endpoints you have on the machine, and you can do that with Globus compute endpoint list. And hopefully what you will see is an endpoint with your name that's in a running state. Now, endpoint, which means that if you did like a PS awk on the node you're on, you should see a process running under your username on the login node that is running this Globus compute endpoint tool. So endpoints can get disconnected, or they can be stopped. If you want to stop the process, it's the same tool you use, Globus compute endpoint. Instead of start, you write stop. And if you need to change anything about the configuration, you can change that and then restart the endpoint, for example. And there's a command that you can do, restart. So that's just a little details of how you can interact with the endpoint. The endpoint has an endpoint ID that's listed here. And this is a randomly assigned UUID that the Globus tool, compute endpoint tool, assigns to your endpoint. And that is communicated to the Globus service. So in our previous example, you can see here we had this UUID, this endpoint ID. That is where this where that came from. So once you set up your endpoint, you want to copy that endpoint ID, and that is what you're going to use on your remote machine to point your client to this process. Okay, So how do you set up the config options? So I just said you need some file, some YAML file with these options. What is that? What does that look like? Well, the answer is it depends on your application and it depends on your use case. So all I can really do is give you a sample example and point you to a few things you need to provide and options you might want to consider changing. I will say there are a lot of options, and in a talk like this, I can't really cover all of them in detail, but I'll just give sort of a high-level overview here.
Kristen,
Yep.
we have a couple of questions before we move forward. So one was like, do we have these Globus supported on Polaris, sorry, on Sophia?
Great question. So, you can run Globus tools on Sophia. You would just need to create a Conda environment or a Python virtual environment where you install this tool. And I know there are people who have run Globus compute endpoints on Sophia. So
Also,
yes.
okay. And then another question is, does the endpoint persistent or does it change every time Polaris is rebooted?
It is not, well, okay. It is not persistent. If the node the endpoint sits on is rebooted, which can happen during maintenance, but doesn't always happen during maintenance, but often does, then yes, the endpoint will get disconnected. And so you need to check after maintenance, you'll go onto the machine and execute this endpoint list command, and you can see the status of your endpoints. And most times, although I have seen processes survive maintenance, but most times, 9 times out of 10, you will have to restart the endpoint after maintenance.
Okay. And just on one more question, do we need to set up the endpoint in system for all of our calculations, or are the endpoints tied to the specific directory?
Oh, so they're not tied to a specific directory. What they are tied to is a specific allocation of resources to workers. So if you have some tasks that you run maybe one per GPU, you might want to have one endpoint for those kinds of tasks. And if you have another set of tasks that you run one task per 4 nodes, those tasks you might want to run with a different endpoint.
Okay.
But they can run, they're not tied to any specific directory. Yes.
Thank you.
Okay. Thank you for the questions, everyone. Okay. So as I was just alluding to, there's different ways of configuring your endpoint. The endpoint will contain all the information the endpoint process needs to submit jobs to PBS. So if you think back to that batch script we started with, you had things like the queue. Oh, the queue, the account where you're charging node hours. These are contained here in the endpoint. You also need to tell it what type of scheduler it's communicating with. In this case, it is PBS Pro. You also need to tell it things like the wall clock time of your jobs and any kind of special scheduler options, which on our machines, I think both Polaris and Sophia, you need to specify what file systems your jobs will have access to. Here, it has access to all of them, Home, Eagle, and Grand. The endpoint will start will launch jobs on the scheduler, and within each job, you will have these worker instances. one worker will run one task at a time. So you have to think carefully about how you assign resources to workers. And that information is also contained in the endpoint config. In this particular example, and again, this is just one way of doing it, we're assigning one worker to one GPU. A Polaris node has 4 GPUs. So what that means is we want all of our nodes to contain 4 workers. The way we set that up is up here with these options. Available accelerators refers to how many accelerator chips there are, in this case, GPUs. So for Polaris, that's 4. And then we set the number of workers we have per node. We'll also set that to 4. We can then also set the CPUs that we want assigned to each worker. Now on Polaris, the optimal assignment of GPUs to CPUs goes in reverse order, if that makes sense. So you want to assign thread 0 to GPU 3. So this is an example of the way you would assign CPU threads to GPUs that will give you the optimal performance on a Polaris node. And the way this is described, it might look familiar if you're familiar with MPI applications. Each set of ranges, thread ranges, for each worker is separated by colons. So we have 4 workers, so you can see there's 4 batches of numbers separated by colons here. The last thing I'll highlight is the piece down here about blocks. What is a block in the parlance of a compute endpoint? You can just think of the block as a job. So what you're setting down here is how many jobs your endpoint can submit at any one time, and how many nodes will be contained in each block. We're running this endpoint on the debug queue, so you can have at most 2 nodes per block. Here we've assigned just 1 node per block. And again, block equals job. And then we've set the minimum and maximum number of jobs that the endpoint will allow to be submitted at any one time. And so for the debug queue, you can only submit 1 job at a time. So we have max blocks set to 1, and we have min blocks set to 0, which means when the endpoint has no work, it will not submit any jobs to the scheduler with min blocks equals to 0. So there's other options here that I'm not going to go into, but if you have questions, we can talk about that at the end. And again, there's other ways you could configure your endpoint based on your application and your workload. This is just an example. Okay, so we've talked about how to just send these like simple functions to Polaris remotely through Globus Compute. However, often with these kinds of remote workflows, you might need to do other kinds of tasks, either before the function runs or after the function runs. And the way you can do this with Globus tools is using something called Globus flows. And so now we're going to talk about Globus flows, which is an automated and managed workflow service tool that's hosted by Globus. It's built on top of AWS step functions, and it's hosted in the cloud. So essentially, you can define a workflow, a Globus flow, and you can send that definition to the Globus service, and it can exist there persistently, and you can just submit, anytime you want to run that workflow, you can make a call, and Globus will do all the orchestration steps in the flow for you. A flow is composed of actions, and we'll talk about the different kinds of actions you can have. So we've just talked about Globus compute, and so you can have a Globus compute action within your flow, but there are other kinds as well. And I will say you can also monitor your Globus flows in the Globus website through their web UI. And this is a little screenshot of what that looks like. So as I was saying before, Globus Flows is a workflow management tool where the user can send a definition of their workflow to exist persistently in the cloud in the Globus service. You can then say, okay, I want to run this workflow. The user says, execute this workflow with these particular inputs. And then what happens? The Globus Flows service will step through the actions of the flow and execute them in sequence. So in this case, this is a sample flow from one of our users with the Earth Science Grid Federation. There's different kinds of actions here. So you might see in the middle here, transfer. So Globus, the Globus service, when it has a transfer action to execute, what it can do is it can look out in its landscape of the different endpoints and processes that are communicating with its service, and it can say, okay, endpoint A, endpoint B, you need to execute this transfer, and it will just do that automatically. Then, following that action, you move on to the next action, which in this case is a compute action. So it's transferred some data between two different file systems, and now it says, okay, I got to run a compute function, and it will then communicate with a compute endpoint, in this case on Polaris, and it will run a function. That function might be using the data that was transferred in the previous action. So you can see this is a way you can couple transfer and compute together in one workflow. So I mentioned there's different kinds of actions. We've talked about transfer actions. There's compute actions. There's other kinds of actions. So for example, you can have what's called a choice action, which is an action that will execute like a decision based on some input of what action to move on to next, for example. And then there's a whole host of actions associated with data management on a Globus collection. So for example, if you want to delete some files, or if you want to change the permissions of some files, there are actions associated with those kinds of things as well. And you can find a whole host of example flows with different actions in this repository here, hosted on GitHub. Okay, so what does the definition of a flow look like? They can be quite complex, and I don't want to like spend too much time on this, but this is a very basic example of a two-step flow that does a transfer action and then a compute action. The flow is expressed as a JSON object, which has this kind of format with these brackets, strings and brackets. And I've highlighted here in blue the definition of the transfer action, and in orange the definition of the compute action, which is called process files in this example. So in the flow, you always have an action that you start with. In this case, this flow starts with the action state transfer files. Okay, so this will be the first thing that executes. And you can see here, there's a bunch of like different parameters, and you'll see these funny like dollar signs. In this format of these JSON objects, these dollar signs denote variables. So we'll see an example in a second. What this denotes is that the user has to provide an input to this parameter to sort of complete this JSON object. You could just hard code like the source endpoint ID here and the destination endpoint ID here, but instead we allow it to be a free parameter, which means like you can execute this flow between, you know, machine A and machine B, but you could also execute it between machine C and machine D. So you can repurpose these flows for different combinations of machines, for example. The action then needs to know what the next action it needs to move on to. And in this case, it's the compute action process files. And then here in this was a transfer action, this is a compute action. So it has a different set of parameters. You need to give it the compute endpoint, the function, a registered function ID for the function you're gonna execute, and then the keyword arguments for that function. And again, these are left as sort of wildcards. These are things you can the user will pass in at the time of executing the flow. And then the final action will just say end true. And this is kind of what one of these flows looks like. And then you can monitor flows using, and I hope this works, Globus's web UI. Okay, hopefully you can all see this. This is an example of the record of a Globus flow that was run by the APS several days ago. And so this is a real example. You can see in this record, you have for each action an entry for the start of the action and the completion of an action. And here, let me sort them in descending order. So you can click on these different tabs and you can see like the inputs that were passed to this flow. You can see different details about the completion of the action, you know, when did it complete this transfer? How long did it take? Things like that. All the information contained within this record, you can query through Globus's Python API. So if you want to like make performance plots and things like that, you can query the service. But you can also just, you know, by eye monitor things by clicking. So you can also assign like tags to your different flows, which can be helpful in querying. And then, you know, you can see here, this is a quite complicated flow. You can see the full definition of it here. So I will just return to the presentation. How do you submit a flow, inputs to a Globus flow to run? I'm not going to go into this in super detail just because, you know, I have a limited amount of time in this talk, but what are the elements you need to submit a flow through the Globus service? One, you need to register your function. So in the example I showed you before, you were just submitting a function, you know, in the script itself. There is a way in which you can register the function with the Globus service. So it will exist in the Globus service persistently. And anytime you want to run it, you can just call the ID for that function. So when you're running with Globus flows, you have to do that. So you need to register any functions that are executed in your flow. You need to start any compute endpoints that will be executing work in your flow. You then need to register the flow. So that is similar to registering the functions. There's a way you can create the flows client and register it. Then you need to create a flows client to run your flow and submit the flow inputs. Now, how you create the client can depend on what permissions you need to run your flow. So in the example we were seeing before with a transfer step and a compute step, you need to establish authentication with the transfer endpoints for the two Globus collections that do the transfer, and you need to establish authentication for the flow for the compute endpoint as well. You can do this if you're just running this by hand on a shell. It's pretty simple. Like you will, Globus will just give you a URL that you'll paste in a browser and you'll enter your auth credentials. However, if you're doing this repeatedly or it's not a human doing it, it's like another piece of software that's doing it, this can look different. So I didn't want to go into the details too much because it's kind of a case-by-case basis how you want to approach this. But there are clients like confidential clients that will take enhanced credentials in order to do this in an automated way, or you can do it sort of by hand. But essentially, to run the flow, you need to set up the inputs. So that, again, will look like a JSON object that, if you recall the flow definition we were looking before, you had all these little $ options. This is filling those in, okay? And you have here, you would have to put in the ID, which would be, I didn't want to paste in a bunch of UUIDs, but you would fill in the UUIDs for these collection IDs, the compute function ID, the endpoint ID, and then if there's any keyword arguments, you need to do that. And then once you have a particular flows client for your particular case, in this case, this is using a specific flows client, then you'll run the flow with the flow input. And you can get more information on these details in the Globus documentation, and there's a nice example notebook sort of doing some of this work here in this repo that you can look at. So the last comment I'll just briefly make, and I sort of alluded to it, sometimes people are doing these kinds of remote workflows in an automated way. And I just wanted to mention, we do offer some different tools to enhance automation. ALCF does offer now service accounts that allow for the easy maintenance of like endpoints that are shared, that are being used by like a service running at an external facility, for example. And then Globus offers automated authentication with something called client secrets. And you can get some more information in their documentation here as well. So we have, for a lot of these automated services, a pattern where people will be running it with a service account and a Globus client secret on our machines. Okay, with that, I will conclude. So what we've talked about today is how you approach the execution of remote workflows on ALCS systems. This is becoming increasingly common on our systems with the new IRI program in Oscar computing, but also with our work on LLM and other inference services for scientific computation. Users at our facility have had success using Globus Compute and Globus Flows to execute remote workflows on our systems. This can work with sort of two levels of tools. One is Globus Compute, which is a fire and forget function model that will send work to Globus Compute endpoints. The Globus Compute endpoint has to be configured by the user on the system of choice, Polaris, Sophia, Aurora. And you need to give it a description of the resource needs for workers and the details of your allocation on our systems. Globus compute functions can be incorporated in Globus flows. This allows for the coordination of compute tasks with data management tasks that are launched from the Globus service in the cloud. And tools like ALCF service accounts and Globus confidential clients and secrets are available to facilitate automation for use cases that require it. And with that, I will end there and I'm happy to take any questions. Thank you.
Hi, Kristen. Thank you. We have a couple of questions.
Okay.
I don't know, Alfred, do you want to ask your questions yourself? You can unmute yourself and ask the question.
Yes, thank you. I have two questions. The first question is the bulk of this webinar already contained in the full workshop, the ALCF hands-on workshop? That's the first question. Second question, about your APS example, do you have to set up a Globus on both APS and Polaris? And then if so, does the file transfer go through a login node? I ask because it sounds like a bottleneck if everything goes through the login node.
Okay.
That's it.
Sure. So to answer your first question, so in the hands-on workshop, there are materials that walk you through an example of running Globus compute only. There's no materials on setting up Globus flows. For that, I would reference you to this example notebook. Oh, can I get my mouse over? Oh, here, this might be a good resource. This is an example showing you how to set up a Globus flow. So the hands-on workshop only contains information on Globus compute. For your second question,
Kristen, before you answer, can you put the link in the chat so other people can
yeah,
access it?
sure, let me see. Oh, all right, let me
The one you just grabbed. Oh, if it's in the slides, that's okay. I thought it's in
yeah,
the
it's in the slides, so
okay,
yeah.
then don't worry about it. Okay.
Okay, yeah. So for the second question, I guess I didn't go into this in too much detail, but so the Globus compute endpoints have to be set up by the user on a login node. The transfer endpoints are different. Typically facilities, such as ALCF and APS, will host what's called a facility endpoint. And if you go to our documentation on data management in the ALCF docs, you'll find a whole section on Globus transfer endpoints. Those transfer endpoints are hosted on hardware separate from the login nodes that have the file systems mounted. So the transfers do not go through the login nodes. So what needs to be set up? So a facility like ALCF, like all of the Oscar compute facilities, have transfer endpoints for their various file systems connected to their machines that they host as a service for their users. So you just need to look up the ID for, say, the Eagle file system. That's all you need to do. And then on the APS side, yeah, the APS has a whole set of computing infrastructure over there. And so they have something similar. They have facility hosted transfer endpoints that they have set up. So transfer does not go through the login nodes. Okay.
Thank you. There is one more question before I get to Fakhor, who has raised his hand. So Nan is asking if the remote machine is using a Slurm, will all the Slurm tags work, for example, Slurm arrays on the provider part?
Okay, yeah, good question. So I didn't really talk about this. So what you would need to do is, so in the configuration, the provider, rather than PBS, you would use the Slurm provider. And I would need to look up the API for the Slurm provider, but I think it should be fully featured. I mean, I believe it is for for PBS, I guess your question is specifically, can you do Slurm job arrays through a compute endpoint, a Globus compute endpoint? I don't know the answer to that question specifically. I would have to look that up, but you should be able to run jobs through Slurm. You would just use the Slurm provider, and I would recommend that you go to the Globus documentation to look up what options they offer for the Slurm provider. Sorry, I can't be more specific. We don't.
No, that's good. And then just to confirm, all the examples you provided are in the GitHub link that is in the slide deck, correct?
All of the examples for Globus Compute are in this
GitHub.
repository here
Okay.
from our workshop. The flows examples are not, but I would reference you to look at this notebook here that gives you sort of a simple example for Globus flows.
But we do have the link for this example. It's still in the slide deck. So you
Yeah,
do have the
yeah,
link.
both links are in the slides. Yeah,
Awesome. Thank
both
you.
links are in the slides.
I see Fakrul Hassan's hands up, so please go ahead and ask your question.
Thank you. Thank you for the presentation. Can you hear me?
Yes, I can.
Yes.
Right. Sorry, I missed the first 10 minutes of the presentation. So I was wondering if we can use this to run softwares that executes a binary, for example, LAMS or VASP, maybe run hundreds of set up one Python app to run hundreds of these calculations, and can we have our own pre-processing steps or Python scripts that can be executed to pre-process some of the data? And can we have dependencies in the jobs so that one job depends on some other jobs?
Yeah, definitely. Thanks for the question. So, you can definitely run compiled executables like VASP. You can follow along, like you would have to create a Python function that wraps around the compiled executable in this way. So you would have some path to the executable on our machines, and then you would launch it in this way within the function. Now, you asked about pre-processing steps or post-processing steps. Depends on the kinds of steps you're doing. So it might be that, I don't know, you need to, maybe you have executing an executable and maybe you need to so in this example, actually there is a pre-processing step in the sense that you make a directory to run the code in. So that's in a sense a pre-processing step. You could, if you needed to do something else, like create an input file to the application, you could maybe fold that into the function of the application, and you would just run it before you launch the command. If you have any kinds of steps where you need to move data between machines, then you would need to use Globus flows. And so that would exist as an action within within a Globus flow, for example. But you could do a lot by just, setting up, different steps within your compute function. If you have certain pre-processing and post-processing steps that need to be done before and after every instance of your application. So to answer your question about dependencies, absolutely. So within the Globus flow, you can, have a chain of multiple compute functions. I mean, in this case, there's a, transfer, compute, transfer, but you could have transfer, compute, compute, transfer, and you could link them in this way. And the second action will only execute after the first action. We do have certain actions, and I didn't go into it in too much detail, called choice actions, which can make decisions based on what you need to do, but it would kind of depend on your use case. Like, I think flows is great if you're kind of orchestrating data movement from outside the facility, but you know, you could also, in this example here, where I'm sort of launching a bunch of tasks, if you had sort of like, you know, task A and task B, and then you want to run, say, task B, or in some cases task C, you could also set up a chain of different task dependencies within your script that launches compute functions. That's another way of doing it. So there's a few different options, and the way you would do it is the way you do it in a tool called Parcel. So you would make it depend on whether the task result has been fulfilled, for example. So you could do it with flows, you could do it by chaining task dependencies in a script like this. I guess I will also say, for the particular case of VASP, we've had a lot of users in the past use a different tool we have at the facility called Balsam, and that might also be something to take a look at. So there's a few different approaches and options, but all of those things are certainly possible to do. I hope that.
Yeah, thank you. And about also, I agree that it's useful for us and calculations, but it just doesn't have an out-of-box configuration for Sophia, which is kind of sad.
Oh, yeah. Okay. Yes, that is true. Although I think if you use the Theta GPU config for Balsam, that might work.
Was from Sophia.
Because Sophia was Theta GPU. It was repurposed. And so there might be
Okay,
some, yeah.
I'll give it
I
a
can
try.
also
Thank
talk to you offline if you need some help with that as well.
you. Sure, that would be lovely. Yeah, thank you.
Okay, wonderful.
Thank you, Kristen, and thank you, everyone. Are there any more questions? I would like to thank our speaker, Kristen, for this very good discussion and talk, and we will provide the slides and the recording available. And I hope to see you guys next year, and happy holidays. Thank you.
Bye, everyone.